So welcome to our prostep ivip web seminar today. My name is Gise and I will guide you through today's web seminar. Our topic today is smart systems engineering, traceable simulation results in heterogeneous environment. Next slide, please. First, let me give you a brief introduction to prostep ivip. It is a registered association, was founded in 1993 and is based in Darmstadt in Germany. And we count about 190 international companies and organizations as our members. And we have committed ourselves to develop modern standards for product data management and virtual product creation. The solutions we provide directly address the challenges that manufacturers and suppliers are facing in these fields. Our technical program consists of approximately 30 projects divided into user-driven topics, implementation support topics, standardization topics, and application benchmarks and communication. And smart systems engineering is part of the user-driven topics. Here for the organizational frame, the conference audio is muted, so if you have any questions, please submit them via the question window and then they will be answered at the end of the web seminar. The next slide, please. Then I will now hand over to Fabian and Stefan, who will introduce our today's topic and our speakers.
Okay, here is Stefan Rude speaking. Next slide, please. I'm introducing as a representative, that means as a chairman of the prostep ivip project Smart Systems Engineering, which generated results we are going to present today. The pictures of the presenters we have seen already are the names are now in the sequence of the talks. That means of the speeches, which we will hear and see in some minutes. Fabian Fischer is the project manager of the SmartSE project, and the other presenters, which are Hassan from Denso, Pierre from PMSF, Peter from Excellence, Kim from prostep, Doug from Dassault Systems, will present the various showcases. And finally, Hans Martin from Bosch will both present a showcase and the summary and the outlook of the project Smart Systems Engineering. Next slide, please. I will start to present an overview of the SmartSE project. Afterwards, we will present 3 showcases by our experts you just recognized. And we will give a summary and an outlook to the SmartSE project phase 5. At the end, we will hopefully have enough time for questions and answers, for a Q&A session, which allows to discuss about interesting topics from your side. Questions can be formulated, as Sarah said already during the presentations, into the chat. This might be questions for the results of the SmartSE project in general. This might be questions to our showcases or questions to the future plans of the phase 5 of the SmartSE project in the next 3 years. And the next slide, please. Numerous project partners have been contributing in the last years to the SmartSE project. It have been always at least 20 partners per year in parallel. So it was a little bit changing during the years from year to year, but it is worth to mention that a lot of OEMs from as well automotive and also from aerospace industries are part of the project, and numerous suppliers or tiers, and together with the OEMs, these are the so-called users in the SmartSE project. A number of IT vendors. The most famous IT vendors we have in the project, famous IT vendors, yes, and numerous research institutes, universities, and academia which work in our field. And last but not least, the experts, the excellent experts who work as service providers and help us really to work on the results, which some of them will present it in the next minutes. The project is open to new partners, so if you are already a member of the project ivip Association, it is easy to participate by a small financial contribution to the project. If not, it might be interesting for you to get a member of the prostep ivip Association, and we know already about a strong interest to participate in the next years from at least 3 additional partners, which are not listed in the logo list, which you see on the right side. So the next slide, please. What is the kernel task of smart systems engineering? Fundamentally, it is a cooperation between partners, for example, an OEM and a supplier. And fundamentally also, it's a cooperation based on the exchange of systems engineering objects. Systems engineering objects which are necessary for an efficient cooperation. In principle, a partner A may delegate a development task to partner B, from which he expects to get a supply part at the end, but very early was a describing model, which we called core model, which is to be integrated into an overall development of partner A. So partner A has to deliver all information which allows a partner B to do his job perfectly. This might be specifications or requirements. This might be optional test cases. In some cases, partner B has to develop test cases on his own. This might be so-called boundary models. That means models around the core model, which a partner B has to deliver. It is expected from partner B to deliver parts at the end, prototypes beforehand. And before that, a model which is already tested in a local environment at partner B, for which he got the necessary boundary models from partner A. But partner A must be able at the end to integrate and to verify or to validate the whole system based on the information he gets from partner B. SmartSE now concentrates his efforts on the exchange of simulation models for this purpose. Because it might also be that only the exchange of specifications or requirements or the exchange of geometry models might be according to the same process. SmartSE concentrates actually on simulation models. Next slide, please. So SmartSE is already running since approximately 10 years now, and phase 1, we started concentrated on the so-called functional mock-up interface on FMI. And we think today this was a strategic right decision, because today it is used for various projects which run into the future of at least automotive industry, we know, but also for the aerospace industry. Phase 2 generated best practices around FMI, about FMI best practices, and a process model around which allows to exchange, or which allows to detail specify what I explained in the slide before. Phase 3 finally dealt with accompanying activities, for example, IP measurements or data management around the exchange of FMI, of simulation models. And phase 4, which we are actually dealt with virtual ECUs, V-ECUs. That means models to exchange also software models for the purpose of a common simulation of FMIs and V-ECUs, for the purpose of simulation-based decision making and what elements belong to it. So at the end of phase 4, all results will be described in a so-called recommendation version 3, which is available by the beginning, which will be available by the beginning of the next year, of the new year. Previous versions of recommendations are already available. They are publicly available via the prostep ivip website, via prostep.org. The next slide, please. What is SmartSE in a nutshell? In the middle, we have the figure which I explained a minute before. But on the upper left side of the slide, here is shown that we started based on the V model, and we started with a description of various processes in the area of software model exchange and the area of physical model exchange. And we did it because on the top side of the figure, you see the need of the coupling different simulation models from different disciplines like 3D geometry models, finite element models, one-dimensional models for multi-body simulation and so on, software models, electronic networks, hardware models, and different simulation tasks can be supported, which are in principle listed below as horizontal bar charts. And very easy ones, for example, deal only with, for example, a 3D model with a finite element model, but more complex ones need more model types. Most extreme complex ones is, for example, in the field of the autonomous driving, where all disciplines are involved and must be coupled together. The elements to do this are shown in the down left corner, which is FMI and SSP, system structure and parameterization. And on the down right side, you see the keyword of virtual ECUs, which are needed to be coupled with such a more mechanical thought FMIs. And down in the middle, we have still the situation in practice that for all the different disciplines, there are different repositories in use in practice. SmartSE project has been concentrating on simulation models, but on the basis of metadata, we worked on links to other models like geometry or software can be managed. But this is to some extent still an open issue and also a theme for future activities. And upright, you see, we should serve for simulation-based decision making, and this is about in the focus of interest of SmartSE directly for the next 3 years. Now the next slide, please. What will we show today? And from the icons you have seen, this is mainly the interaction now of SSP with FMI, first showcase, which we will see in a minute. In the middle, a more complex process between an OEM and a supplier, which builds up a simulation based on the specification of SSPs, the delivery of FMIs, the execution of a simulation, and the traceability of both process and also the data which are needed and which are generated. And last but not least, the third use case shows that the approach is not only usable for mechatronic issues in kernel, but is open and usable also for other physical domains like thermal simulation, but also for other IT vendors which are today eventually not in the line. So as Sarah said before, questions are allowed during the session via chat and will be answered at the end of the webinar. And now I would like to hand over to the first showcase directly to Hasan Essen from Denso Automotive. Please, Hasan, it's your stage. The stage is yours, this way around.
Thank you very much, Stefan, and hello everyone. Welcome to our webinar. I will introduce you how we can use SSP and FMI standards for parameter optimization as first showcase. My name is Hasan Essen from Denso Automotive, Germany. After giving a short background, I want to also briefly introduce you the SSP standard. I believe maybe for some of you it is not known. And afterwards, I will directly start with the short demonstration using FMI and SSP standards in which we developed a transmission control unit. Then I will conclude my talk. As a background, Stefan already introduced that when we are dealing with complex system design, this requires often collaboration between engineering teams, which in return means also exchanging simulation models between these teams. These teams can come from the same company, or it can be also between companies. So in our proof of concept that we developed, we wanted to see how SSP and FME standards can facilitate, can support this kind of collaborative development environments. Let me briefly introduce you the SSP standards. First of all, SSP stands for System Structure and Parameterization. This is developed by Modelica as a Modelica Association project. The purpose is to provide a tool-independent standard to define a complete system consisting multiple one or more functional mockup units, and also includes their parameterization. As a structure, SSP is actually a simple zip file, but the zip file contains several other information. It, on one hand, contains complete system information with all related resources like FMUs and so on. But on the other hand, it consists several sub-formats in XML. And from these formats, the system structure and description, the first one you see here, is the only mandatory one that you should have in an SSP. This basically defines a hierarchical and functional structure of this network of FMUs. In addition to this, you can, of course, have also different XML files defining system parameters, or if FMUs have a different naming for same parameters, you may need a kind of parameter mapping, or if you want to collect control signals in a central location, you can also signal the dictionary. But as mentioned, these last three are optional files. Okay, after this brief introduction, I will directly go to the use case. As mentioned, in this use case, we developed a transmission control unit collaboratively. And your use case story is that an OEM gives to us, to supplier, specification of transmission control unit. And together with that, the OEM delivers the remaining parts of the vehicle model. That includes, for example, engine model or some powertrain related other components. So these are packed into FMUs. Is given here FMU engine and FMU vehicle, and together with the spec, these are delivered from OEM to the supplier. And on the supplier side, based on the requirements, so we developed a transmission control unit and also packed it as an FMU. So what you will see in the demo is that how we pack now these components together, how we integrate them together, how we can perform there some kind of parameter variations and to test, for example, robustness of this transmission control unit. And the final of the story, of course, then after this is done, it should be packed and sent back in an IP protected form back to the OEM. Before I continue, I would like to also underline that this is actually an example use case. So there was no real OEM involved. However, the models we use is the realistic high fidelity models with complex parameters and functions included in those FMUs. Okay, so also let me show you before starting the demo. This is the final architecture we would like to achieve in our SSP system. As I already mentioned, we have three FMUs. Engine and vehicle are delivered by OEM, and they were developed by Siemens Amesim tool and exported as a standalone co-simulation FMU. And on the other side, we in the Denso side developed the transmission control unit, and this FMU was this model was developed in MATLAB and then exported using Modelion tool as an FMU. So after using these authoring tools and creating the FMU models, so we needed an integrator to create this SSP system, and for that we used PMSF FMI bench tool to create this integrated SSP system. Okay, now I will start one by one what we have been doing here. So this is, as you see, the tool interface. This is the PMSF FMI bench, what we used for integration. So the first thing we need to do is that using this tool, we can create a SST project. And once a SST project is created, we can import the already delivered FMUs from OEM first into this architecture. There's this import function, so we are here importing these ones, and through import you may also give, for example, any name you want to give or which signals you want to give. You can make this kind of selections. After we imported the OEM FMUs, we also go to the model that we developed. Similarly, it's also imported. Yes, so basically that's as a first step we are done. So in this case, we basically created now SST project. As you see in this figure, we imported 3 FMUs. But as you see in this, the status now, they are not connected, these FMUs, with each other yet. That's what we will do in the next step, you will see. So now we want to integrate these ones. So as you know, in like tools like MATLAB and Simulink, you can, these input and output ports of the different blocks, you can just connect. This is actually what we do is a very, very similar way. Here is as connector for each FMUs, different input and output ports are listed. And as it was shown in the first architecture picture, so we have this specification, we know which input signals should go to which output with drag and drop. So these signals can be mapped with each other. So this simple step basically allows us to connect the components together, and that's then the picture then we reach. So basically now we connected and everything is now kind of ready. Actually, in this case, we can already simulate this system. We have our integrated system ready. However, we wouldn't be able to observe any signals, or we wouldn't be able to vary any parameters right now, because we didn't describe how we will interface those with the outside of SSP architecture. So that's what is necessary. So once you packed and connected together, you need to define the link to the outside world from SSP system. That's what we do. The so-called, we will now expose these connectors. And so all this is actually a very kind of rather straightforward. If you go, you will find a command that to expose the connectors, and then this will give you the opportunity to all output signal lines to export. And one thing is that later on, these exported signals, we want to reach them, we want to visualize them using any script, or we want to modify them maybe. So if you want to do something like that, it would be also a good idea to give, not to use directly the names as defined in the FMUs, but you can of course rename them and make it simpler. You can make your life simpler than for later on to reach to these signals. Okay, but when this is done, basically that's what we will reach. So when this is done, what we did is, as you see in this picture, now it was connected, and also from now all of the output signals, we now link this to the outside of the SSD. So we can now observe those. Okay, so the next one, so what we need to do is that now we have the signals to observe. However, we cannot still edit the parameters. So there will be some parameters, of course, many parameters in the FMUs, and you want to vary them. For example, in our case, we want to vary some parameters from engine and vehicle, and then we want to see if our TCU or transmission control unit is robust for these changes. This you do in a similar way. First, from each FMU, you make also, in addition to the input-output connectors, you also make the parameters within this FMU to be exposed to your SSD architecture. So this you do for all of your FMU components. Whatever parameters you have, you can expose them. And once you did this, you will do those next step, like in the signals, also from this SSD architecture to the outside world. Also, you can make them visible. You can choose which one you want to be visible, and then you need to export them, expose them. When we do this, so we will see here now in this list, not only the input-output signals, but many other parameters are here listed. That means that they're exposed also for the outside world. Once we completed this, there is one last step before we can simulate. We want to create a standalone simulator. And for that, we use the function that FMI bench from PMSF provides. And that allows you to export all this packed SSP as a standalone simulator. So we do, including all the resources. So that's what we do as the last step. We export this, and during export, of course, you can make some parameterization, and that brings us to our final step, basically. That's what we now have. So not only the signals, we also have now access to the parameters from the vehicle and engine and TCU FMUs, and we exported it as a standalone file. Now this file simulator, we can move it to any, this is tool independent, we can move it to any computer and we can run it basically directly. That's what we did. That's shown in this next figure. So this you can run it basically, so from a command line. So you go to your folder where your simulator is, then basically as you execute any other executable file, you run it. It offers you some parameters to add and change. so that you can run the simulation with different functionalities from the command line. -H is, for example, you see help. So and when you see here, you can also edit, for example, start time, stop time of the simulation, or some kind of high-level, system-level things directly from the command line. Yeah, then you can, for example, with these kind of commands, you can give a output file destination, so a CSV file name. So what happens then when you run the simulation, giving these destinations, the simulation starts, and at the end, all the output will be stored in this file where you can go and see what happens. Okay, so this was 1180 seconds, I guess, simulation. So it runs, sometimes it finishes and saves the data. Of course, this is good, so you can repeat it one by one and create such files. However, what we wanted to do is different. So we wanted to run the simulation loops and make the parameter variations so that that's automatically kind of done. For that, we created a loop using Python script, and we used Jupyter Notebook for this. So we could define, for example, for the engine size between 1.5 and 2.1 liter, we can vary the engine size between these two levels, and also vehicle mass. We can also vary, and we can run the simulation in loop without like any manual interruption. And then later on, we could see the results and check if our control unit for transmission does the things it should do. Here, one very simple example, I can show the results. So if you keep the engine size constant, for example, and increasing the vehicle weight, we see that since the engine size is not enough, so we need more downshift in the car, which we would expect. And also other way around, if the vehicle mass is constant but the engine size is growing, so we almost know we don't need the downshift at all, for example. So it does kind of what we expect. So like that, we can make the variations and check if our transmission control unit works properly. Okay, so before I conclude my talk, I want to also underline one point. So what we want to do is we don't want to be, of course, let's say, one of the aims of using the standards is to be kind of also tool independent. So we wanted to check if this SSP architecture can be visualized or run in another using another tool. So kind of to check interoperability, and for that we checked this with Easy SSP tool from Excellent Solutions, and that was possible. So once you create the SSP architecture using one tool, you can use any other tools that are compatible with SSP standard. You can also import it there and work with another tool. Okay, so then let me conclude by my talk. So we created the SSP architecture, and with 3 FMUs with many parameters to vary. So what we could see that its parameter handling features are quite well, and it allows us the flexibility to expose these parameters. And also it has also possibility to hide if you don't want some parameters to be visible. So it also from the IP sensitive information can be hidden. And so I believe that therefore these standards will play a core role and an important role for to deal with this collaborative complex system development tasks. We will keep on working on this for example, simulation data management point of view, or how we can create this SSP architecture automatically. And also traceability is another issue. So we will continue working on this. But at that point, also related to traceability or showcase 2, will show you some good results. So with that, I would like to give it over to Pierre to introduce you showcase 2.
Thank you very much, Hassan, and thank you for presenting these results that also employed our tool FMI bench, so Pierre May from PMSF IT Consulting. And I have the pleasure of introducing the second showcase. So as Hassan already demonstrated, SSP in combination with FMI already allows you to easily complete simulation tasks across tools, so decoupling the modeling tool from the system architecture tool, from the simulation building, and allow you to achieve portability in this fashion. The next showcase will demonstrate this in a slightly larger context, so not only at the level of being able to exchange models and so on, but in the context of being able to do so in a credible fashion, so in an ordered process, and what SSP and extensions above SSP can do to help you achieve that. So if we look at the current status of usage in simulation, I think we can all agree that we do quite a lot of simulation nowadays. We do have great tools and not so great tools, but we know that there are great tools available. We have great modeling languages, for example, standards like FMI that allow us to exchange stuff without sticking to one modeling language. And we tend to have a lot of experience in the various domains that we have established simulation use. So in that sense, everything looks hunky-dory. We trust our simulations. We have an understanding of the benefits and drawbacks of certain modeling approaches and so on. So that's actually quite good. However, increasingly, if we look at the future, we are faced with the question of how do we convince others to trust our simulations? Because really, decisions are increasingly based on the results of simulations, and decisions have far-reaching consequences. And we are now talking about, for example, validating products, mostly using simulation in some cases, in some instances, but at least partially doing this in simulation and not only in real-world testing. And for that to work, not only do we have to be convinced that what we are simulating is proper and right, but we also have to have a way of demonstrating that to outside instances and to the public at large, that what we are doing is something that we can stand behind. So the question really becomes, how do I transport this belief in the validity of my simulation to the outside world? And the key question there is, how do I convince others about the credibility of my simulation results? So it's not only do I believe in them or are they correct, but can others also believe that they are correct? So are they credible in their eyes? In order to do this, we have to answer quite a number of questions. So, for example, what was the goal of the simulation? What were the requirements? Which steps were performed? What models? Why these models? How was the output processed? And so on and so on and so on. And these are just a couple of the questions that arise here. So what the SmartSE project then focused on was going beyond the kind of collaboration model that Hassan already demonstrated. What is really necessary in order to be able to easily and reliably answer these kinds of questions in a transparent fashion? And there are two parts that we see in connection with this. The first part is really we need a common understanding of the overall simulation process. So something like a credible simulation process that divides simulation tasks into individual phases and steps that can be performed with individual details, of course. I mean, every kind of simulation task will vary in its details, but that there is a common framework in which we can really talk about what is happening, what needs to happen, what are the interdependencies between the different phases and so on. And here inside the SmartSE project, an instance of this, the so-called credible simulation process was developed and defined, and has actually in parallel also already been validated inside the set-level project, an ongoing research project that's federally funded in Germany, where many companies are participating in order to come up with a simulation tool chain for the development of autonomous driving systems, for example. And there, this process has been adapted and has been put through its paces in order to see how and whether it fulfills the goals that are behind it. And the second step to this is when we are performing such a process, lots of information is being generated along this process chain. And we really need to collect all of that information in a way that allows us to glue it together to provide comprehensive answer, not just individual information pieces. And that's where the so-called glue particle approach has been defined to try to collect that kind of information in reusable structures and in standardized structures that allow the easy exchange and interchange of those kinds of information chains. And the one special focused area that we are focused on is how to put something like this on top of SSP, because SSP already helps us in providing containers for exchange of data and various techniques for addressing resources that are needed. And for traceability purposes, for the group particularly, we kind of need the same kind of capabilities of being able to take all of the disparate parts of information and piece them together, provide metadata, provide their interrelationship, and exchange them between tools that are part of the overall tool chain, because the whole assimilation process will never happen just inside one tool or even just inside one partner company. It will span tools and companies, and hence we need an easy exchange of all of the partial information so that we can collect it in a good way. And the SSP traceability specification based on SSP, but extending it towards simulation task metadata, so to speak, is trying to achieve this. And this forms the basis of what you will now see in the rest of the showcase, where we take the credible simulation process and we take the STMD and SSP traceability specification, and we run through a simulation process where individual partners and individual tools will collaborate. So you will see tools from prostep, Traceable, Excellent Solutions, EasySSP, Dassault System, Daimler. Our FMI bench tool is being used in the background together with Excellent Solutions tool, and again prostep Tracy, to cover the whole credible simulation process for a simulation task. And for the purposes of this demonstration, the simulation task is a fairly simple one to look at, to keep the demonstration simple. So we're talking about a pre-selection of a DC motor for mild hybrid applications. So we want to select a motor for a drive unit. So this is a pre-selection kind of decision. So we're not validating the final product, but we are making decisions on the further development. It's a component level decision, and the focus will be on the suitability of the component. But again, wrong decisions at this early stage can lead to large costs later on. If you later on find out you picked the wrong DC motor or it is not as capable as thought. So the credibility of this kind of simulation still is a question that is relevant, because you have to demonstrate, for example, to an OEM that the component selection at your level really makes sense and something that they can base business decisions on. And with this, I would hand over to Kim Steinkirchner from prostep, who will take over at the beginning of the overall process and demonstrate the analysis of the simulation task and objectives and tracing.
Thank you, Pierre. So hi, I'm Kim from prostep, and what you will see in a couple of seconds is the tool Tracy, which is developed in the context of the research projects that Pierre also mentioned, and it is especially designed to work with the credible simulation process and to support the documentation and exchange of simulation results. And in this showcase, the Tracy user will be the overall customer in the project around the pre-selection of the DC motor, and they will therefore define the simulation task and the objectives of the whole project and the requirements, then hand over to the guys responsible for the simulation, and in the end do the evaluation of the simulation results and then decide if all the objectives have been fulfilled. And to do so, we have a look at the tool. And at first, our user needs to create the project that we want to work with. So we create a new project via the button over there and decide to do this with the credible simulation process, which is a template in Tracy. And the resulting project then looks like shown here. On the left-hand side, we have a tree view that shows all the phases and steps of the credible simulation process, starting with the analysis, with the sub-steps, then the requirements phase that we will go into, and in the end, the fulfillment phase. And on the right side, you have a graph view of everything shown on the left-hand side, plus extra resources that we will soon add here. And if the user clicks on anything, in the left or in the right, then on the further right, there comes the detail view, which shows details on everything, for example, that we used the credible simulation template. So to start everything, the user jumps into the analysis phase, and there to analyze simulation tasks and objectives. And here we already have an artifact added that shows the simulation tasks that Pierre introduced. And to have a detailed look, we open this artifact and go to the external resource compartment here and download the PDF that was placed there beforehand. And in the PDF, we can then see that, yep, we're here for a pre-selection of the DC motor for the mild hybrid application. And we also have some parameters that will later be used in the simulation. So this is the overview of the task we're going to see. And based on this task, the user will then create a requirement, just an example requirement now, for the simulation model. And to do so, the user goes into the assignments of the step. So assignment is an artifact that is added to the step, and we decide that it shall be output of this. So the resulting requirement to work further with this, we create a new artifact and name it model requirement, totally generic, and choose the qualifier to be requirement, so the tool really knows this should be a requirement. And then the user adds which physical effects should be considered for the model and which effects should just be neglected and other details like that. And we create the requirement. And then we take the simulation task and the requirement and export it as an STMD file, so a glue particle. And do this via the button and receive a downloadable file, which the user can then send over to the guys responsible for the simulation. And in our case, that's Peter. So here you go, Peter.
Thank you, Kim. Let me just introduce myself. I'm Peter Lobner, a software architect and project lead of the EasySSP SSP model editor built by developed by Excellent Solutions. Yeah, now we will go on and switch to the design phase of the simulation, and I will show you how the design, the software simulation architecture is created in EasySSP. So Kim, just click next, and then we will start. Once the simulation task and its requirements have been specified in Traceable, the information stored in the glue particle is transferred as an STMD file within the SSP container to the partner responsible for the simulation. In our example, this partner acts as a simulation system integrator. The simulation engineer opens easyssp.com in the web browser and loads the SSP file into Orhideo EasySSP. So at first, the engineer needs to get a deeper understanding about the simulation task. Therefore, they open the integrated glue particle process view, which shows the current status of the simulation process with its phases, steps, and resources. Then, to familiarize with the simulation task, they navigate to the analysis phase and open the simulation task documentation and have a look into the details. So the data Kim provided in the first step. Then the engineer reads the simulation requirements previously defined in Traceable. And now that he or she understands the task, they are ready to start designing the simulation architecture as SSP. In the EasySSP model editor, the engineer defines the system architecture, starting with a component providing stimuli for the simulation, and then a system element for the system under test. Then he or she adds the relevant interfaces, including data types and units to those hull elements, and then the connections between the connectors. To achieve a clear design, the engineer uses waypoints for the connections. All is based on the SSP standard and so fully transportable to other SSP compliant or compatible model editors. Then they go on and model the system under test with its inner elements, connectors, and connections. let's just wait until the system architecture is complete. Yeah, if they want to provide further design infos for the model, they can do so by adding detailed descriptions to all model elements. For example, a connector. As there is the requirement to evaluate different internal resistances of the e-machine against each other, the engineer adds a parameter variant for all resistance levels to be tested. In this case, we want to evaluate the resistance levels 0.05 to 0.5 ohm. To easily add parameters to the model, the engineer imports them as SSV files. That's SSP standard compliant file format for the exchange of parameter sets. Then the engineer assigns the parameters to each simulation component and parameter variant. The actual parameter variation is accomplished utilizing SSP's parameter binding feature that allows to override existing parameters, in this case, the internal resistance level of the e-machine. So for every parameter variant, a dedicated resistance value is specified, as you can see. So now that the system architecture design is complete, the engineer exports the SSP file that now contains all implementation relevant information, the system architecture, its parameterization, and the process information stored in the STMD file, and hands it over to the partner responsible for implementing the simulation components. In this case, that is Doug. Doug, I hand over to you.
Okay, thank you very much. So my name is Dag Brick, and I have taken the responsibility of implementing the models of our example. So next slide, please. So we are in the Daimler environment here, and we can open an SSP file, the SSP file containing our architecture, like this. And from that, Daimler will create a Modelica package and convert the system description into a Modelica model and import any FMUs that were present. But in this case, we have just an empty project. We also import the simulation task metadata and its associated documentation, and that will support us in the development process. And here we see the top level model. It has a stimuli model and a system under test. And the system under test contains an e-machine and the load, the mass. And what we have here from the SSP file is the system architecture, that is the components and the interconnection structure. And we go into the e-machine now, and then we create the behavior model in here by dragging and dropping standard components from the Modelica standard library. And then we have to connect all these components up and connect them to the predefined inputs and outputs of the SSP model. And in this process, Daimler will then propagate units and quantities from the behavior model to the connectors of the enclosing system. And then we do the same with the mass system, connect some components, and that is done then. And now we are ready to generate FMUs for the different components. We have several options here for generating different kinds of FMUs, co-simulation, model exchange, and include different bits and pieces. One of the important steps here is that we have to select what variables we want to expose in the resulting FMU. And in this case, we decide to expose parameters and output variables. And of course, the inputs have to be exposed as well. And now we can compile the model into executable code and build the FMU. And just to be on the safe side, we run a test of the entire system and sweep the parameters. So we now select the variable that we are going to study, which is our evaluation criteria, and drag it over. And then our sweep parameter, and enter the values that we're going to sweep, like this. And then we can run the simulation and look at the results and see if they make sense. And now when we have done that, we can take an extra look at the documentation and see that everything seems to be okay here. And that means that we have completed the task of creating our simulation behavior models, and now we're ready for the next step in the process. So I return to Peter.
Thank you, Doug. Let's go on to the next phase. Now that Doug has provided the simulation components to the simulation system integrator, we can start to actually integrate them. So Kim, next slide, please. To do so, the engineer loads the FMUs provided by Doug into the existing simulation architecture in ECSSP and compares them with the specifications. Here we have an FMU for the stimuli, for the e-machine, and for the mass. Just wait until this is ready. So then to document the implementation of the simulation components, we add the documentation provided along with the FMI components to the model implementation step in the process here. Then we go on and insert information about the successful integration to the integration step, in this case, another Markdown file. And as quality is very important for the simulation task, the engineer adds then a predefined rationale describing the quality assurance actions that have been taken to achieve the demanded quality standards. Now the implementation phase is finished and the model is ready for simulation. So let's switch to the execution phase. So next slide, please. In the simulation execution phase, the integration engineer simulates the model repeatedly and compares the different parameterizations. Due to the fact that the model is defined as SSP, one can load and simulate it in other SSP-compatible simulation environments, like, for example, Dassault Daimler, BMSF FMI Bench, AVL Model Connect, or DSpace Sonic Model Management, to just name a few. In this case, the simulation engineer decides to use ECSSP's cloud-based simulation engine that is built on BMSF FMI Bench. Here, the simulation engineer can simulate different parameterizations in parallel in the cloud with no load on the computer. To do so, he or she opens the simulation view and creates a new simulation by clicking on the Simulate button. the first step, you choose which parameter variants to simulate, then configure the simulation options on global or individual run level. In the last step, one selects the desired hardware configuration from a list of available options and chooses the maximum simulation duration. And now for every parameter variant of the SSP model, a simulator is generated, deployed in the cloud, and executed. All this runs in parallel. While the simulation is running, you don't have to wait for the results, but can proceed working. In the meanwhile, the current status of the simulation is always visible in the Model Explorer. And during the simulation, all status details are shown when clicking on a step. And you also can watch the current simulation results during execution if the simulation takes longer. So after simulating different settings and parameterizations, the simulation engineer shows the results in the results view. And here you can resize the charts or zoom into the data to better see the details. This helps you when you want to compare the different parameter variants with each other and choose the best results. If the integrator is happy with the results, he or she can choose one or more simulation runs and store them with just a few clicks in the glue particle. And since all relevant information like model, config, and results are stored inside the SSP container and the STMD file, the simulation engineer can reload the SSP model later to show the results and simulate the runs with the original settings. And after completing the simulation phase, the engineer exports the model as SSP and provides it to the person responsible for the evaluation. And that's, in this case, Kim, back to you.
Then, hello again. We're now in the final two phases of the credible simulation process, which is the evaluation of the simulation results and then decision about the fulfillment of the simulation objectives. And here the Tracy user will spot check some of the results that were provided by the simulation integrator and conclude the whole process. So let's do it. At first, the user needs to load the SSP provided by the system integrator into Tracy. And they can do this via the project list in Tracy, via this button, import an STMD file or an SSP container. And the imported project then looks like this. We see again the process information that was in the glue particle, and we also have all the resources that were used by the system integrator, plus the resources that the Tracy user, him or herself, created here. So let's now do an evaluation. For this, the user now especially wants to check in on the quality assurance. So they move to the quality assurance step in the implementation phase, and there check the document on the setup quality that was provided by the system integrator. The user goes to the resource information and downloads the provided markdown file to check in if everything was in order. And let's say to the user, this all looks sensible. So everything was done as it should have been done. Every quality measure was taken that needed to be taken. So this is all fine, and the user can move on to the execution phase and check into the results. So into the assignments, and here into one of the diagrams of the simulation runs, which can also be downloaded from the resource information and opened, and the user can have a look at the diagrams that we just saw. They all seem to be good for the user, so the execution was fine as well. And then the user can note down the evaluation results, so their thoughts on if everything was okay or not. They can do so by adding another artifact, as we already did in the requirements phase. Again, an output and a new creation and another generic title like evaluation results. But another qualifier, this time the qualifier is a rationale, because this is really thoughts of the user on what happened. And the text is that the simulation was executed correctly and that all the results are credible to the user. And with that, the evaluation phase is then done in this example case. So the last thing that's needed is the fulfillment phase. And for that, the user can use the overview that Tracy provides over all the process steps that have been taken and all the resources that were either created by the user here or by users in other tools. And with this, the decision can be made that in our case, we think that the simulation was done fine and that the goals were successfully reached. And this can be noted down in another artifact in the same way as was done in the requirements phase and in the evaluation phase. But for now, we'll skip this because it's just the same steps again. Everything was done fine. So the next thing is, what happens if not everything was totally fine? What if the user encounters a problem during the project? It might, for example, be that he's on a coffee break and another simulation user and someone from another project comes up and says, we've always had problems with one specific model in our project. I cannot remember the name correctly, but you might better check if you have any connections to our project and see if your model has the same problems that we have, because it might be the same model. To do so, the user can then use the impact analysis that Tracy provides. And the impact analysis is basically a graphical representation of all connections and relations between elements in Tracy, elements that were created directly in Tracy and elements that were imported via SSP and STMD. And in this information, the user then can filter for specific things. For example, was our model reused in other projects, and where exactly was it used? So we'll do an impact analysis with one of the models that we used in our experiment here. So the user goes to the implementation phase and there to implement models, where the models were put down as the artifacts. And the user can go to one of the FMUs and open it in Start Impact Analysis. What you see now is the impact analysis with different filters. For example, for entity types, so we could choose artifacts or projects. We could choose specific artifacts like the requirement or rationale we had. And you could choose different relationships like import, output, or a requirement. And in our case, we want to know if there is a project using our model. So we select projects and we go to the maximum depth to really see everything and apply the filters. When we have applied the filters, we see that the model, in fact, is used in other projects, in another motor example, in DC motor example, which is us, and in the project XYZ motor, but not in the project that the other user mentioned, which would have been project ABC. So at least for this model, we're safe. We don't have a connection to the project that the other one warned us about. And we can still say we reached our simulation results and we did not have any problems. And with that, I'll hand over to Pierre for the conclusion of our showcase. So Pierre, here you go.
Thank you, Kim. So to conclude, what did we see? So the whole purpose of this showcase was to show complete traceability from requirements to simulation results, but not just in the usual fashion, but rather in a way that, I think I'm stuck actually. Kim, can you switch one step further? Thank you. So this was based on a standardized approach. So all of the artifacts that were exchanged in terms of models and system structure were SSP based, and all of the additional information that needed to be transferred, additional documents, inputs, procedures, rationale, output documents, were transported using the SSP traceability extensions. And to emphasize, no proprietary bridges were needed. So all of these 4 tools were able to cooperate without each tool knowing about the other tools. There's no Daimola, EasySSP bridge or Tracy, FMI bench bridge or whatever. All of them just do standards compliant data exchange using standardized formats. And the other benefit that this also entails is that we've seen that, of course, certain information must come from the simulation engineer by manually providing, for example, rationale information. Why did he do certain steps or in what way? But other information can automatically be filled in because it is automatically generated as artifacts, as inputs, outputs during the simulation, and hence can already be automatically recorded inside the traceability. So that's the one thing. But what Kim already showed in the last step is that if you have this kind of information base, especially not only across one project, but across multiple projects, multiple iterations of projects and so on, using this standardized data exchange, you accrue quite a number of interesting pieces of information that allow you to then do analysis based on that, to do error impact analysis we were seeing, or error cause analysis, so where did an error occur, where did it arise from, what do I need to fix in terms of my artifacts or in terms of my processes to prevent it from reoccurring. How can I reuse certain models, for example? How do I find those models? How do I find the relevant metadata for the models? Were they validated? If yes, for which purposes, and so on. So this gives you another level of increasingly improving your processes. And of course, if we are able to create this kind of feedback loop, reuse traceability and QA analysis really leads to an increase in reliable simulations. So that's the same thing that we've seen in manufacturing, is that the moment you are able to measure and to close the loop, you can increasingly increase your quality and your processes and try to achieve something like a zero defect strategy. And that's what we really want to see happening in this space. And that's also why I'm actually very happy that the Smart Systems Engineering project, with its approach of trying to foster standards-based interchange and then providing and developing the processes that are needed to really make industrial use of those standards and further those standards, really allows us to do something like this and create a baseline. And again, it's not about the 4 tools that you were seeing, but of course, I mean, we as manufacturers of those tools are very happy that it's those 4 tools you were seeing, but really based on the standards, this allows any kind of tool that wants to support those standards to be integrated into this kind of landscape. And that's why, continuing with this, we really want to invest in this approach. And here on the last slide of this showcase, you can see the next activities that the individual companies are planning in the space of SSP and SSP traceability in order to move this forward. And we really would love for more companies joining. I mean, already more companies are supporting FMI and SSP, and SSP traceability is for us one of the next steps. So please get in contact with us at the SmartSE project or with individuals, and if you're interested in this approach. And with this, I think I can hand over to Hans-Martin, who will take over with the next showcase.
Thank you, Pierre. Well, my name is Hans-Martin Heinkel. I'm from Bosch, and in the third showcase, I would like to introduce you the workbench concert hall, which was developed and is used at Bosch. The main focus will be how the glue particle approach can be integrated into existing infrastructure like the concert hall. The concert hall is used for various simulation tasks such as thermal design of control units. Commercial as well as self-developed tools are used. You see here a selection of these tools. Special workflows have been developed and various applications have been built up of these workflows. And we use here from ANSYS, the OptiSlang tool. And what we did, these workflows we make available to the user via apps you see here. The user then selects the specific information like project, electronic devices, layouts. We can then, for example, simulate the impact of different break profiles of an ASP system on the thermal behavior of the ECU and get the results. So that are typical simulation use cases we use at Bosch, not only in the beginning of development, also for verification and validation of our products. So these workflows are quite common and broadly used in our company. So the result and the generated report, as well as the information required for traceability and replay, are then available here. As an extension of the traceability functionality, we want to make the information contained in the simulation tools available as well. So most simulation tools have all information which we need for traceability. So what, for example, are the tool version? What are the solver settings? Are inside the tools, and most of the tools are able to export that in the moment in proprietary formats, and the ordering is also proprietary. So what we have done now in a first step, we use here the ANSYS metadata extraction feature for a first prototype to extract this information. And what does the integration of the glue particle approach look like? We are scripting the automated export of the relevant information, both from the ECU Twin Maker and from the automated ANSYS metadata extraction is carried out. After that comes the splitting from the information from here into the special chapters of the glue particle. And then comes the storing of the glue particle in the SPDM. That happens in the background without any additional effort for the user. This is a very crucial point for the acceptance, because in the moment, traceability often means that the user have more to do and the acceptance is therefore low. That is a point what Pierre already mentioned. So we have really to take into account that most of the information we have to generate automatically and fill up the necessary information sheets for traceability automatically. So as less effort for the user as possible. What have we seen? Infrastructures like the concert hall uses very heterogeneous tools or IT environments. It was shown that an integration of the glue particle approach into existing high automated infrastructures is possible. And the glue particle is not limited for simulation using FMI and SSP on system level, but can also be used for simulation on geometry level or for other engineering tasks. We also show that an integration of tools which are currently not directly support the glue particle approach is possible. Now I want to summarize the showcases, and I want to give an outlook of the SmartSE project for the next years. So what have we addressed? The usage of standards like FMI and SSP, how traceability, reuse, automatization, search, analyze functionalities can look like, and how that can work in cooperation between several partners with different IT and tool environments. Topics which are also important in simulation-based development and validation. We need processes recommendations for cooperation of several partners, and how can we deal with abstraction and modeling, and what does we need for the reliability of simulation results, and what should quality standards and recommendation for simulation look like. These topics we address in the phase 5 of the prostep SmartSE project. This slide was already shown by Stefan in the beginning. Now the phase 5 is added. Our goal for the phase 5 of the SmartSE project is to support the enabling of collaborative development and validation of complex products by simulation along a multi-tier supply chain. In the next 3 years, we will deal in the fields of considering the simulation along the supply chain, dealing with abstraction and modeling, cooperation of system engineering and agile methods, and the extension of the V model to more stages of the life cycle. The concrete work packages for the next years are: in the work package 1, the simulation quality. The topics will be the extension of the SmartSE reference process and the credible simulation process for a multi-supplier chain. And here a deeper evaluation of the glue particle approach for traceability along the supply chain. Also, how to assure appropriate simulation quality with respect to the criticality of the simulation-based decision. This is a follow-up activity of the white paper, Simulation-Based Decision-Making and Release. In work package 2, we develop approaches how to handle different levels of abstraction when using simulation in-house and in cooperation with a chain of suppliers. That means how to get an adequate abstraction and detail level of a simulation, how to assure validness of simulation models along the supply chain, and how to connect virtual verification and SysML. In work package 3, we will identify how system engineering and agile approaches complement each other. The topics will be like how to ensure traceability when using agile methods. Are end-to-end approaches feasible? In work package 4, the topic will be to extend the V model to further lifecycle phases. We will identify the needs for action, for example, as resulting from updates over the air, or that field data feeding back into the product development. Very important points also will be how to validate a system against a limited set of requirements, the so-called technical controllable system in system, versus how to validate a system against unlimited unknown requirements, the so-called open world problem. Work package 5 will be the central hub for getting actual information about relevant standards and give input to the according bodies. That means we will use it for the SmartSE internal collection of requirements for standards like SSP, FMI, virtual ECUs, and to get an overview and make the preparation of external activities, for example, with METI, YAMA, System X, ASA, Modelica, ISO. And if you're interested in these topics, get in contact with us and perhaps, and we hope so, join the SmartSE project group. Now I hand over for the discussion. Sarah, it's yours.
Yeah, thank you first of all to all the speakers for this interesting web seminar. Yeah, we are now open for questions. So if you have any questions, please submit them via the question window. Yeah, and there's a first question already. Could SSP be also used to deliver the TCU specification or interface to the supplier?
Okay. So, okay, if we can use the SSP to deliver from OEM to supplier, use the SSP to define what the specification is. That's the question. So yes, actually, that can be done also in the SSP. So as I mentioned, at the end of the development cycle, so as it's transferred as a whole block, the whole overall system as an SSP block to back to OEM. That could be also considered at the beginning together with the FMUs, some additional files defined in some, that could be some parameter specification or could be some other extra files can be included and packed under this zip and then delivered by OEM to supplier 2. Maybe it's not considered, let's say, SSP for this purpose, but can be done.
I will also make an other comment on that, because that is really the step in the direction of traceability of simulation tasks. So with SSP, we have now reached the standard that we can formalize the design phase. So we make the system structure and can transport that system structure in a way that can be simulated and can be used directly for the implementation. But still, there are missing elements, and because you normally need some by information, and that we address with the glue particle approach to enhance the SSP exactly with this kind of by information, which can be some textual information or some visual information or something else.
Okay, thank you. And then we're waiting for more questions to come.
Maybe to add something to what Hans Martin was saying while we wait for more questions. As you said, this is exactly so transferring this kind of architectures is one of the key reasons for SSP as well. And as you said, usually you want to have additional information. Something that we didn't showcase in the showcases because we wanted to keep stuff simple is that the formats that can be transported here are not just simple markdown formats or pictures or PDFs or whatever, but actually the better standardized information you can exchange, the better for the overall process. So SSP, of course, as in the SSP base standard, supports multiple formats that can be used, and it's actually open-ended in this regard. So, for example, if you need to transfer additional requirements in a specified way, transporting them as regif files, for example, that is the standardized format for exchanging of requirements, would be something that is fully capable of doing, and that would be the advice way of doing it if you can. It's just that we didn't want to get into all of the other standards that are out there and complicate the showcase, so it's mostly markdowns and PDFs in that case. But really, the more you can use standardized formats here, the better, and that's something that we want to foster. And that again goes back to the overall message of SmartSE, I think. The more we can foster the use of standardized formats together with standardized processes and standardized industrial experience, the better the level of system engineering we can achieve, and the better the level of simulation credibility we can achieve. So definitely anything that tries to go in this direction would be something that should be compatible with these approaches. And if it's not, we should make sure that we make it compatible.
Okay, thank you. Then there's just another organizational question. Will the webinar video will be available afterwards? Maybe I can answer that. That will be, yeah, maybe will be available on the prostep ivip YouTube channel, but yeah, I can't tell you the time frame. Okay, there's another one. Which role play tools like ePlan or format like eClass for the concepts you have shown here?
Well, I can try to answer. So as I know, ePlan is on the level of for the electrical planning of industrial buildings. So it's a different level. So in my, I'm not totally sure, but it's not directly on that simulation level. We saw the showcase with the DC motor, but for the glue particle approach, it doesn't matter, and that was what we tried to do with our first prototype within Bosch, that we really integrated total different simulations and only use these frameworks which support us by the glue particle STMT approach. So with that approach, we think we can also, like the SSP in the moment, it's basically using FMIs, but it's open for all other simulation models on signal level and also on energy level, so an acausal simulation. But that will be further steps.
Yeah, maybe to add to that, so there's two parts to that, I think. There's the SSP level, and as Hans Martin already said, I mean, the SSP standard itself is already open in the sense that you can plug any kind of component theoretically into it. Currently, the connection infrastructure is mostly focused on signal level and certain acausal information. The ongoing development work for SSP 2.0 will try to broaden that to other areas, and so anyone interested in that work is really welcome to join the Modelica Association Project SSP, which is the standardization organization that does the SSP standardization. And there have been ideas to broaden this quite a bit further. And then there's the second level, that's the traceability extensions. And for now, we build them on the SSP platform because we think there's a good reuse of the infrastructure there. And especially in areas where SSP already is useful to use, it's a very good next step. But theoretically, that SSP traceability extension is also applicable even if you don't use any of the SSP base functionality. So you can trace information without using, for example, system structure description diagrams to couple models and so on. So in that area, I think definitely this can be even more decoupled. And there I would really want to point you to the SmartSE project in the next phase, because broadening the scope of what the SmartSE project is looking at also into different broader domain perspective or open world problems, the interaction with agile methods and so on. I think those topics will be of interest to you in that regard maybe, and that's also currently the home where much of the impetus for the traceability specification is coming from. The pure standardization side of that will probably at some point in time land at some standardization organization. But right now, I think SmartSE is a good docking point for getting to these topics. And I think there are also partners we've seen. I mean, there's a heavy concentration of automotive companies currently as SmartSE project members, but there's also aerospace companies and there's industrial companies like Siemens, for example, and they have much broader topics in mind there. So I think you would find also interesting cooperation partners at that level.
I think it's good to add some words and sentences about the working mode of the smart system engineering group, because we try to integrate all the different aspects of system engineering. That means processes and how can we combine simulation and all standards around that. But in the SmartSE group, for example, we won't make a new standard for simulation for example, FMI or these things. So here we are in cooperation with organizations like Modelica, and in the Modelica organization, they make the FMI, they make the SSP. And what we do in the SmartSE group, we try to give the feedback from the industry and try to make in prototypes the connection between system engineering processes and these things. And that is what we are going for. So for us, it's very important that we have a good network to other organizations, because we can only be the integration point and give also the feedback to these organizations. Perhaps, Stefan, you would also add some words to that point.
Of course, Hans-Martin, that is a working mode we have since years, that the industrial requirements are discussed. And as I said in the beginning of the seminar, of the webinar, we were lucky to start with FMI. We have now the situation that we believe that SSP is a good approach to glue FMUs together, FMI-based FMUs together. But we know that with the showcases today, we could only show a very small deeper look into specific problems. If we want to integrate software models, yeah, you could add the ideas on OSMPs and things like that. Or if we want to look a deeper look to the FMI by co-simulation and what solvers are needed to be integrated with software related approaches, we still know that in the area of simulation models, we are a little bit at the beginning in a situation where we were with a CAD technology maybe 30 years before, something like that, where prototypes could be reduced because the geometric compatibility of parts which were assembled from suppliers could be done in a first shot without any discrepancies, without any overlaps, without any problems, and to reorder parts from suppliers. The same happens today with verification and validation based on physical prototypes, where the behavior of the physical prototypes should be perfect in a first shot, but this requires that simulation before gives us the chance to judge if behavior models, if simulation models fit to each other and work together without resulting in too much errors or incompatibilities or effects which we don't want to see in the final product. So simulation technology is, in my opinion, today still in a phase where an intensive cooperation between experts is needed to make a really benefit of the approaches we can use based on digitalization.
Okay, thank you. And there's another question. How can I perform an impact analysis in case I need to know which requirement has a relation to which work products, like design or implementation?
The relation is always built based on test cases. Requirements based on test cases, which are the starting point in the credible simulation process for the simulation, which are done to prove that the requirements are fulfilled.
And you can, of course, do so in Tracey and select a starting point, either the requirement or the thing that you want to check if it is affected, and then set the filters to find everything that impacted or had the impact.
And another point, because in the moment we often talk about information lake or information ocean. But if we have the information in an atomic structure, in my opinion, we are lost. And if we want to make an impact analysis of an ocean of atomic information, that is very difficult. And what we do here with the glue particle approach, so we have a standardized basic structure. So we know the chapters and the steps, and we know what kind of information can be stored. And here we can make the query checks, and even we don't know in before what we are looking for, but we have set pre-structuring with our informations in that standard. And that will be a very, very powerful mechanism which can be then, for example, used by Tracey. Otherwise, in the status today, we often have to pre-configure our databases and can only search for things we had thought before. And that's the way we are thinking here, because we have these basic structures which should be standardized and which can be enhanced. And that is, I think, is a very powerful mechanism.
Maybe the only thing I would want to add is in the showcase, we only showed the core structure of the interrelationships. So all of the different individual information pieces were structured according to the process. So you had requirements, and they are an input to the design phase and so on. But that's at the overall aggregate level of information. But what the traceability approach also provides is the ability to provide additional linking information, so that you can, for example, link at a very fine granular level, that you can provide this kind of information of saying this specific requirement is embodied in these specific parts of that model, or in these specific decisions in that design decision base. And so this is using an XML linking technology that provides outside linking deep into the individual formats. So that from our point of view would of course be the next step that you want to have. The reason the traceability information is structured like it is to ensure that even if you don't have that specific information, at the very least you have the aggregate level information of that you can point to. These requirements were the basis for this design step. But of course, the better and the more fine granular you can provide that information, the better. And there are mechanisms in the traceability specification that allow that. It's just not something we have showcased here.
Because in reality, we has also an hierarchical set of, for example, processes. So we have the simulation process, then as Doug showed, we have the modeling processes, and they are somehow connected. And that can be up to unlimited levels, how deep that will go. And that must be supported by the traceability, and that is what we want to achieve with that approach. And therefore, we need exactly the things what Pierre mentioned.
I think it's also worth pointing out that SSP and the glue particles by themselves are flexible enough to accommodate many different application domains, different kinds of processes, and different kinds of corporate standards. So even though we have demonstrated one particular set of tools and processes in these showcases, they can be adapted to essentially any other corporate environment or development environment.
I think that's just a starting point we saw today. So that really generic formats you can adapt to the use cases you have within your company. So that was just one style on a high level we showcased today, but you can really go into more details with linking mechanism with different file formats you can use. So it's really a generic way you can adapt to your certain requirements you have. within your company. And by the way, just to give this hint, the features you saw today from the EasySSP side will be available this at end of this year, but that's just a starting point. So it's the beginning of a journey, I think.
Okay, thank you. Then there's another question related to Showcase 2. When we want to build up such a process, what part will be the most difficult one?
Depends
that
on the
depends on your
perspective.
background and your previous
We have to
experience.
pick one.
May I answer in the beginning as an engineer with a lot of good and also painful experience. So normally the simulation process, well, we have still some difficulties because something doesn't work so proper. But the main problem is the first two steps to get the proper information. What does I really want to simulate? What is really my task? And what should be neglected? What should be taken into account? What are the KPIs? And especially in the beginning, this is very floating, and it's an iterative process, and it's often very painful if a software engineer comes to for example, to the person and he says to him, well, I need a camera model for testing my software function, and it must be a good model. And these are the typical discussions. And that is not a technical problem. That is a problem between disciplines and between who is responsible for what part of the process, and where we need some stronger cooperation. So
I would fully agree with your, I would fully agree with your position, Hans Martin, that the first step is the most complicated. The understanding of the engineering task, the understanding of the simulation task, the deep understanding of what is wished by as an answer from the simulation. As we started to prepare the showcases, and I have seen showcase number 2 the first time, it was my proposal that the engineering task should be explained with some more words, because it was very well known for the people around us. But as a person who must understand what is done, it's very important to give the time to understand the simulation task first. Otherwise, you are lost to understand the simulation results. Otherwise, you are lost to interpret the curves and results by the end. And I would fully agree that the good understanding for the simulation task is the most complicated job in this story.
And one thing that we haven't discussed is if there is any knowledge or perhaps older solutions available within the company that could be reused or at least act as inspiration. And that is like an extended scope of the traceability concept, to be able to maintain knowledge and transfer knowledge between generations of engineers within the company.
I would
Good point.
add that at a meta level, I think the first step is always the hardest. And I think that's going to be key. And that's also something that we kept in mind while designing the traceability approach, is that in order for any approach like this or any improvement to work, you really have to get people on board to actually do the first step. Because initially you have to do something more than you maybe did previously. So the time between you do something more and you get a benefit out of that really must be reduced. And that's why, for example, this traceability stuff is very scalable, in the sense you already should get a benefit if you, as Stefan and Dark said, if you just start by recording the sketch of what the simulation task is all about and noting down what you were informed about, in a very simple file format and stick it together with your simulation models and so on. That's very basic traceability. So you're missing out lots of functionality that the traceability stuff might give you. But even just this and archiving this together with the results would already improve your life much in the next step by the next reuse or by transporting that information to a colleague if you are going on holidays or whatever. So I think one of the challenges for an organization introducing this is going to be the change problem of trying to convince people that it's worth doing slightly more work to get a better result. And I think that's where we have to concentrate to really make this as simple as possible so that you very quickly get a benefit. And then you get into this virtuous cycle of the more you do, the more benefit you get, the more you will be willing to put into it. But the first step is going to be the hardest, whichever one you pick, I think.
Okay, thank you. Then another one. In a multi-tier collaborative environment, do you have a recommendation to make sure that outdated files are not used in the different tools by the various parties?
I think outdated is an interesting word. I mean, also being a bit philosophical here, but because every step, and that also includes the failed solutions and the failed reasons and the failed discussions, the ones that ended up as a dead end, they are also interesting in the global scope. And should of course be preserved, if nothing else, as a lesson learned. Then of course we have the issues of version control and configuration control, and then we go into the territory of PLM, perhaps more than system engineering. And I think all of that fits together, but these are kind of orthogonal concepts, and just the way that you need your version control and configuration management to manage CAD data, or you also need that for simulation data and for system engineering models, and not the least, of course, for software.
I would add some points here, because this is one of the core elements or things we want to achieve with the glue particle approach, because what we have in these glue particle, we have set requirement, and we have set version of the data sheet, and we have set and set versions, and our result is based exactly on set status of the information, and set and when something changes, we can see, oh, well, something changed. We have to make a new simulation, and we have to put in a new requirement, or we had to put in other parameters. But that is what Doug said. The simulation is still valid according of the old requirement, and perhaps 1 year later there will be another project where we do exactly need this kind of information or this result. So the glue particle is also already always valid along that snapshot of information or that baselining which is connected to that. And that is exactly what we want to preserve with these glue particles. So if we have millions of these glue particles or these mechanisms implemented, we can really see, well, we have done that, so there will be no dead ends and not outdated information, but we surely have to look, has something happened, has something changed, so we have to resimulate or make that job again. But we can trace if something changed, but we can keep the old information, and we will keep the old information.
Okay, thank you. Then there's one last question. I understood that the test cases you are considering to assess the credibility of the models are only simulation-based, for example, evaluate the results for different values of parameters. how physical tests fit into your framework. Is there any plan to link traceable information from tests to the models?
Certainly. So I think this is just another artifact of the showcase concentrating on a small sliver of the space. So right now we demonstrated this because this also tied into Hassan's showcase by doing parameter variation to do robustness checking and so on. But certainly, for example, for a DC model that models in a really existing DC motor, you would expect that measured results from a test bench would be applied against the simulation outputs. And that would also be recorded in the validation data. So definitely, this should not focus just on simulation per simulation's sake. You always have to anchor it against reality. And all of the tasks that you undertake to do that should be reflected in what you record in the traceability.
And
So
also, this is what I said in the very beginning of our session, that the task between an OEM and a supplier is always that the supplier has to deliver at the end a physical part, a control unit, a sensor, whatever. And it is, of course, a task of the supplier to ensure that the model he or she delivers is validated against the real part which are delivered at the end of the story.
And that is the main part. So there was a question in the beginning, what is the most difficult part? So in my opinion, it is the beginning, but it also the verification and validation process of the whole tool chain and of the results. Because here we need system experience, product experience, together with the experience of the simulation expert. And that is another very crucial point, how to guarantee, well, my simulation is valid. But on the other hand, if we have a real test bench, it's the same. How can we why do we trust the result from a real test bench? It's exactly the same kind of problem.
And then the problems that were mentioned in the questions actually come together, because what really happens in practice is that at some point in time, someone did take the trouble of trying to validate that model against the test bench result and so on. But then the question becomes, is this still valid? Because the model was enhanced, was used in a different setting and so on. So the question then becomes, we do have validation results, but do they match what was being used in the overall system simulation? And that's really where traceability then comes into the picture, of saying, yeah, it's all nice and good, as Kim showed, that there are documentation out there that say, yeah, this was fine and this was performed and so on. But the quality assurance step then becomes to try to find out, does it trace? So is the validation valid towards the requirements that were being put, or towards the integration environment? So is it being used, for example, inside the range in which the model was validated, or are we using it outside of that range? So all of these things come together, and where traceability comes into the picture is trying to draw all of those individual tasks and individual inputs that are needed to produce credible information together to form a credible whole picture. But definitely the individual tasks, they are still very, very relevant, and there's much more to do than just trying to do traceability. But if you lose the traceability, then all of your effort might have gone to naught, because you did very much work, but you can't demonstrate to someone else that the work is relevant, for example. And that's one of the key problems we are also seeing, is that there's lots of stuff being done. Remember the slides I showed? Individually, you might even be convinced that what you are doing is good and well, and it might even be the case, but how do you demonstrate that to an outside person, to an outside entity? And
if you look,
that's what we have to do.
At the next phase, there are at least 6 points which are addressing exactly this topic. So what is a really practical, good, proper abstraction level we need? How can we validate? How can we trust in simulation? So traceability is only one point, and we have to address a whole bundle of these topics.
Okay, yeah, then I think we can conclude the discussion. Yeah, thank you again to all the speakers and also all who joined and listened to this web seminar today. Yeah, then the web seminar session will continue in 2022 and will start in the end of January with the topics on the CAX implementer forum. And then hear you next year. Stay safe and have a nice weekend. And goodbye.
Thank
Come
you,
join us.
Goodbye.
Bye.
Have a nice
Thank you for your
weekend.
time.
Very much.
Goodbye.
Goodbye.